I've graded your midterm exams, and your grades should have been posted by now. And overall, the class did pretty well. The median was an 84, and the third quartile was like a 92. So that means 25% of you scored over a 92, and Q1 was 71%. So 3/4 of you got over 71%, and maybe a quarter of you got below that. But overall, I'd say the class performance was good. If you were disappointed with your midterm score, sometimes that happens where you feel like you studied hard and you just didn't get the score you wanted. I don't want you guys to be discouraged. I think sometimes when you're in school, it's easy to put too much emphasis on grades and test scores and things like that. And sometimes we just have bad test days, and it's unfortunate that we have to evaluate you on somehow, and testing is like the only way that's kind of practically possible. But at the same time, you as people are much more than your grades and what you're doing in school. Okay, so I know some of you are really trying to get a certain grade in the class because maybe you want to go to graduate school or med school or whatever it might be. And I just want to remind you that it's okay to get a quote bad grade. It's okay to even fail a class. Your life is not determined by the grades you get. You can have a fulfilling life even with bad grades. There was when I was in college as an undergraduate student, there was one quarter where I failed all but one of my classes, and the last class I got a D in it. It was a disaster quarter, and I thought, oh man, this is the end of my academic career, and I really felt that way at the time. But it was okay. It did delay my academic progress, as failing a bunch of classes would, and so that happens. But life goes on. You'll still advance, and if you don't give up, you can still accomplish whatever. And maybe certain doors close because of certain things, and that's okay. I truly believe wherever you end up, that's where you're supposed to be headed. And so don't despair. Grades are not worth sacrificing your mental health for, or your integrity for. You always want to be proud of the journey you take. So for most of you, you guys did fine, and you're happy with where you stand. But if in case that's not the case for you in this class, or even some other class, don't put too much emphasis on just some number here. Okay. All right. We'll continue on in our section here on Chapter 7. A lot of people had questions about the final exam. Is the final exam cumulative or whatever? So I'll say the final exam will have a much heavier emphasis on Chapters 7, 8, and 9. Okay? So final exam will have a heavy emphasis on Chapters 7, 8, and 9. There will be, about 20% of the final will cover Chapters 1 through 6. But that 20% will be conceptual or definition-based questions, and will not involve calculations. Okay? So you don't have to worry about memorizing, or still needing to memorize the standard deviation formula. Okay? But if somebody asked you, what does the standard deviation do, you need to know that it's a way to measure spread in a set of data or something like that. Okay, so chapters 1 through 6 on the final will be conceptual, and chapter 7, 8, and 9 will consist of the main bulk of the final, and there will be definitely calculations involved for chapters 7, 8, and 9. But chapters 1 through 6, about 20%, all conceptual there, okay? And I know for some of you, the conceptual questions were the ones that were the hardest, so, make sure you get that kind of ironed out. If you want to take a look at your midterm exam, you're more than welcome to do so during office hours. But again, please send me an email to let me know that you want to take a look at your exam, because right now, everyone's exams are just in this mess of a pile, and so if you come to office hours and you say, I want to look at my exam, it's going to take me time to go through that pile and pull out your exam. So if you send me an email ahead of time, I can do that work of going through the exam and finding it, and I'll have it ready for you when you come to office hours, okay? So that's all. Just send me an email. I'm happy to show you your exam so you can review it. Okay, any questions before we get started on today's topic or content? All right, then we'll start in chapter 7. On survey samples and particularly sampling distributions. Okay, so this is kind of our first section in the topic of statistical inference, okay? Well, we will get into that. And so I think, on our first day of class, I said we have this thing called the population. The population is too big for us to observe directly, and so we take a little piece out of the population. This little piece, this is our sample. Okay? And we observe our sample, and based on what we see in the sample, we make conclusions about the population. Just get this saved here. All right, so let's let me talk about this concept of a sampling distribution, okay? So what is a sampling distribution? All right, so let's say we have a population, and we've got a categorical variable. Oops. Okay, and what the sampling distribution is that from our population, we draw a sample, a random sample, okay? So I'm going to just call this a random sample. And what we do is, in this sample, because it's a categorical variable, we're going to have a count of successes. And this is just kind of an arbitrary label. So, maybe it's like the categorical variable is, does someone have black hair or not, okay? And we can label, quote, if someone has black hair, that's a, quote, success. And if someone does not have a black hair, then it would not be considered a success. It's just a completely arbitrary label. It should be yes or no, but over time in the literature, the terms success and failure have come around. It could be, does someone wear glasses, yes or no, and one of those you would arbitrarily label success and the other failure, okay? And then so we would have the number of successes, n would be the number of observations. And you would get a p hat, which is x over n, your sample proportion. Okay. And so in the population has proportion p. Okay, so it could be in the population 35% of people wear glasses. I have no idea, I'm just making that up, okay? So when you take a random sample out of that population, okay, so if we said in the population 35% of people wear glasses, and I take a random sample of 100 people, I would expect something around 35% of my sample to be wearing glasses. But because it's a random sample, maybe I get 31 people wearing glasses. So then my sample proportion would be 31%, okay? Does that make sense? All right, and with the sampling distribution is we repeatedly draw multiple samples. So we go sample, we get another sample, and so I'll call this one sample 1, and this one will be sample 2, and here I get another p hat, okay? Then we go to the population again, and we get another sample, sample 3, and I get another p hat, okay? And we repeat this. Repeatedly draw samples, and for each sample, record p hat. So that's what we're going to do. We repeatedly draw samples, and every time we draw a sample, we're going to record p hat. And we do this thousands of times. Okay? Do this many, many, many times. Oops, sorry. Okay, and then and so we keep track of all of these p hats, and after all of these p hats, we will have a distribution of p hats, and that's going to be our sampling distribution. So we keep track of all of our p hats, okay, and we will, have a distribution of p hat values, okay? So, after thousands of samples, we'll have thousands of p hats, one p hat for every sample. And if we keep track of all the different p hats we observe, we have a distribution of p hat values. This is called our sampling distribution of p hat. Okay, so I just want to make sure conceptually that we're okay with this idea. Okay, so I'm going to do a kind of a computer demo of building a sampling distribution, okay? And so the way, what's going to happen in the computer demo, I'll let you guys finish writing this. So what's going to happen in this computer demo is that we're going to have kind of this giant machine filled with Reese's Pieces candies, okay? So we've got this, this machine, okay, a machine full of Reese's Pieces candies. Okay, so if you're not sure if you don't know, if you're not familiar, Reese's Pieces are like M&Ms, except they have peanut butter on the inside, or something like that. And they come in 3 colors. There's orange, yellow, and brown, okay? Okay, so, and I think, let me pull up the, Reese's Pieces sampling distribution. Uh-oh. Is the internet broken? All right, let's try this. All right, sure. Here we are. Okay. Okay, and so what we have is, so we've got this big machine, and we're going to say in this machine, we're going to know that exactly 30% of our candies are orange, okay? And so here I'm going to just draw a random sample of 50 pieces of candy out of the machine, okay? And it's going to sort them orange pieces over here, yellow and brown pieces over here, okay? And so here we go, and it's just pulling out 50 pieces of candy, okay? And so after 50 pieces of candy, we can count these, and we see, you know, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 pieces are orange, okay? 14 divided by 50 is 28%, okay? And so we're going to record a dot. We're going to create a dot plot down here where we put a dot at 28% or 0.28, okay? I'm going to do this again, okay? So in this case, 15 pieces were orange, okay? So in the population, so what we're saying is that in the giant machine, exactly 30% of the candies are orange, okay? We drew a random sample of 50 pieces. 50 of the 15 were orange, so 15 divided by 50 is 30%. We draw a dot at 30%, okay? I do this again. And here, I count them up. I have 17 orange pieces. That's 34%, okay? And we can just do this over and over again, okay? So here, 14 pieces, another 28%. Okay, so I have 2 dots now at 28%. Okay, here, 14 again, so I have another dot at 28%. Is this okay? All right, so I can kind of speed things up here. I'm going to just do 5 samples all at once, all right? And it just shows us the last one, okay? And so here we got 5 samples and we get more dots here, all right? Here's another 5. All right, so this is after 15 samples. You know, we've seen, it looks like 26%, 28%, 30%, 32, 34, and this looks like, I don't know, 38% or something like that, okay? All right, so I'm gonna do kind of We'll do 10 at a time now. So now I'm going to add 10 samples, and so I happened to get one that was 22%, and after 10 more dots it looks like this. So what do you think is going to happen? So here's one. This doesn't happen very often, but here we only had 8 pieces that were orange. Okay? Random sample of 50 candies, only 8 of them happen to be orange, so my sample proportion is 16%. Okay? And so that's going to put a dot right here at 16%. All right, let's just kind of speed things up. I'm going to do this 100 times. I'm going to ask the computer, draw 100 samples, so it's going to add 100 dots to our dot plot here. Okay. All right, so this is after another 100, we have a total of 135 dots in our dot plot, and we can see right now 32% orange, so that's 16 out of 50 pieces being orange. 32% orange is kind of our most common value right now. We'll do another 100. And we see after another 100, 30% and 32% are the most common values that we've gotten. And we're just going to keep drawing more and more and more samples. Okay? So this is after 1,000 samples. I'm going to so at this point the dots have all kind of gotten so close together that they've merged into lines. Okay, this is after 1,000 samples. Here's another 1,000. This is after 2,000 samples. After 3,000 samples. Okay, so this is after a little over 10,000 samples. Okay. What do we see here? Okay, what we see is 30%, 28%, 32%. These are kind of the highest values. These show up most frequently for the sample proportion. Okay, so that means when I drew samples of 50 pieces of candy, I very frequently got 15, which is 30% orange, or I very frequently got 14 orange pieces, which is 28%. Or I very frequently got 16 orange pieces, which is 32%. Okay, also with decent amount of frequency, looks like basically between 24 and 36%. This happened quite a bit between here and here. And values of only 16% orange did happen, but just not very often. Okay, values of getting something like 44% orange, also it happened, but with lower frequency. So we see a unimodal and almost symmetric distribution, something that looks very much like the normal distribution. Okay, so if I superimpose a normal distribution over it, we see it matches very closely to the distribution that we have. One thing you'll notice is that this is not a continuous distribution. Why is it not continuous? Why am I not seeing values like 31%, or for that matter, 31.5%? Why am I only getting values like 30 and 32%? Because we're looking at this proportions based on the number of candy pieces that we have. So you're either going to get 15 orange pieces or 16 orange pieces. It's a whole candy, okay? And so if you have 15 divided by 50, that's 30% orange. If you have 16 orange pieces, 16 divided by 50 is 32% orange, okay? You can't have 31% orange because that would require 15.5 orange pieces, which is not possible. Okay. When we just say how many pieces ended up orange, that's going to be a whole number. Right? I mean, you might get some kind of factory reject, but that's still going to count as a whole piece. Okay, so that's why the actual distribution is discrete. It's not a continuous distribution, but it looks very similar to the normal distribution. Okay, And so from here on out, we're going to look at sampling distributions, and we're going to say we can pretty much approximate this sampling distribution with the normal distribution. Okay, that's what we're going to say. But this is the sampling distribution. And we can change this. We can say, well, instead of getting 50 pieces of candy, what if I only drew 20 pieces, let's say 30 pieces of candy? Okay, what do you think our sample will look like then? Okay, with 30 orange pieces of candy, so this is after 10,000 samples, we still get a very similar shape. It still looks pretty close to the normal distribution. This is what the normal distribution would look like, and we see these lines line up almost very close to that. And we just have a little bit more spacing. If we look at this, our distribution goes between about 10% to about 50% orange, okay? As far as the amount of spread. The amount of spread when we have 30 pieces of candy seems to go, anywhere from 10 to about 50%. If I'm drawing 100 pieces of candy, let's just take a look. We'll do 5,000 samples. We'll just have the computer do it right away. Okay. With after we'll do another 5,000. After looking at 100 pieces of candy, all right. Again, it looks very much like the normal distribution. We look at the amount of spread we have, and it seems like most of our values that we observe are between about 20% and 40-something%. So as we increase the number of pieces total, as we increase our sample size, the amount of spread seems to shrink as well. Okay, but overall, our sampling distribution, these are the different p-hats we observed. That seems to follow a normal distribution here. Okay, so in this case, we have a machine full of Reese's Pieces candies. We're going to say, in the machine, the proportion of orange is equal to 0.3, or we'll say P is equal to 0.3. This is the population proportion. Okay. We repeatedly draw samples. And calculate p-hat for each sample. Okay, and then we keep track of the p-hats using the dot plot. So let me just go back and do so in case you want to do this yourself, I'll put this in our slide here. and so this is our resulting sampling distribution. Okay, and this thing looks very much like the normal distribution. All right, conceptually, are we okay with the idea of what a sampling distribution is? Okay, so it shows us, the distribution shows us the probability or how likely we are to get certain values of p hat. Okay, so we're going to look at how frequently we get a certain sample proportion, a certain p hat, when we go to our population and draw a random sample. Okay, and so so the sampling distribution of p hat can be approximated with the normal distribution. Okay, that's what we're going to establish here. We're going to say that this distribution this one right here, we're going to approximate it using kind of the normal distribution here. Okay, so every normal distribution is defined by two parameters, right? Now what are those two parameters that you need? If you had a normal model problem, what are the two parameters you need? You would need to know the mean of the normal distribution, and you would also need to know the standard deviation, right? Okay, so to approximate the sampling distribution with the normal, okay, we need to know the mean and the standard deviation to use. Okay, and so our mean mu is going to equal p. So what is p? The population proportion. Okay, so we're going to use the population proportion. Okay, and that makes sense, right? If in the machine 30% of the pieces of candy are orange, whenever we take random samples of candy, we would expect about 30% of our candies to be orange, right? And that's what we see. We'd see in the center of our distribution, the most common value we see is 30% orange, okay? So machine is p equal to 0.30 orange. Okay, and what we see that p hat equal to 0.3 is the most common value in the middle. most common value, and is in the middle. Okay, that's what we see. All right, and our standard deviation, our sigma, is going to be equal to p times 1 minus p divided by n. Don't worry about how we got this, but this is going to be the standard deviation for this thing. So where n is the sample size. Okay. All right, so let's just try a problem out here to check our understanding. All right, so we'll say, so in our machine, okay, again, you've got, so now I have a machine of M&M candies. Okay, and we'll say the proportion of candies that are blue is, we'll say exactly 18%. 0.18 in the machine. Okay, so we have a giant machine of M&M candies. 18% of the candies, you know, we counted them all, there's exactly 18% of them are blue. Okay? You take a random sample of, we'll say, 60 pieces of candy. And we're going to ask, what is the probability that over, we'll say 25% of your sample was blue. Okay, so you're going to take a random sample of 60 pieces of candy out of the machine. What's the probability that over 25% of your sample is blue? Okay, and we'll say, you know, answer this using the normal approximation for the sampling distribution. So what do we need to do to get started? So we have to create our sampling distribution. What does our sampling distribution look like? So our sampling distribution is approximately what shape? Okay, so our sampling distribution is going to be approximately normal, which means it's going to look something like this. Okay. What is the value that goes in the middle of our sampling distribution? What's that? 18. Okay, 0.18. So whenever we take a random sample, we're expecting 18% of our sample to be blue, right? In the population, 18% of the candies are blue. Okay, so whenever we just take a random sample out of that, we would expect something around 18% to be blue. Okay, but it's a random sample, so maybe you get more blue candies than that, maybe you get fewer blue candies than that. Okay, we want to know what's the probability that because of just from random chance I get 25% or more blue. This is what the question is asking. What's the probability that I end up, whenever I take a random sample, I'm expecting something around 18%, but because it's random, maybe I get more than that. And I'm asking, what's the probability that I end up getting 25% or more being blue, that over 25% of my sample is blue? Okay. Does that make sense? All right, so we can say we have a normal distribution. The mean is equal to what? 0.18. Our standard deviation is going to be what? P times 1 minus P over N inside the square root. So I'm going to have 0.18 times 1 minus 0.18 divided by N. N is 60. So let's see what this turns out to be. Okay, so I'm going to have square root of 0.18 times 1 minus 0.18 divided by 60. Okay, and I have 0.04959, so I'll just write 0.0495, what was it? 598, okay. Okay, almost 0.496, all right? So now I have I have my mean, I have my standard deviation. I'm going to get my z-score. What do I plug in for my z-score? 0.25 minus 0.18 divided by 0.049598. Is that all right? Okay. So we're gonna I'm gonna do 0.25 minus 0.18, and we're gonna divide by. I'm gonna just plug in. I'm gonna hit answer key because that's gonna plug in the value that I had from the previous computation. Okay, and I get z equal to 1.411. Okay, so this 0.25 is now equivalent to z equal to 1.411. Okay, because the table that we have, the z table, only goes to 2 decimal places, we'll just round to z equal to 1.41. And I want to know what's the area to the right of that. Okay, so we'll look up our z table here. So if I look up 1.41, I have 0.9207. So that's over here. So that means over here I'm going to have 1 minus 0.9207. So the area above, area to the right of 1.41 is 0.0793. Okay. So our answer to this question, what is the probability that over 25% of your sample is blue? I'm going to say 0.0793. So a little bit less than 8%. So about 8%. Okay, this is an approximate answer because we're approximating the actual distribution, the sampling distribution with the normal distribution. But it's pretty good. Okay, it's going to be close to that. So again, the concept is, we know that exactly 18% of candies are blue, of M&M candies are blue. When I take a random sample, I'm expecting something around in my sample to get about 18% blue. But because it's random, I might get more than that, I might get less than that. And what this says is that I've got about an 8% chance that 25% of my candies are blue or more. Yes?
This only works if it's normal distribution?
So this, I guess there's a theorem that maybe I should explain in a little bit, is that when we're talking about a categorical variable and we're talking about the sampling distribution of p hat, which is what we're talking about here, we can approximate it using the normal distribution. There's a few certain conditions that we need to talk about, but that's coming in just a couple minutes here, okay? But I just want to make sure conceptually we're okay with this idea of calculating the probability of getting a sample that looks a certain way. Okay, why don't we pause here for a few minutes. We'll take a stretch break, and then we'll continue on. So we'll say about 5 minutes here.